Good morning, class.
Good morning.
Welcome to you out in TV land. We're glad you can join us today. Let's review some of our elements that we need to know for the test on Monday. Everybody with me?
Yes, sir.
Okay. Riley.
Selenium.
Good job. Brett. Good job. Naya. Nope, not ooh. Yes. Nicely done. Maven. Very well. Scandium. Noah. Nice.
Argon.
You got it. Blakely. Yes, David. And Peyton. Across the back row, Blakely. Noah. Maven. Nah, just kidding. Good job. Riley. Brett. Naya. Virginia. Oxygen. Beryllium. David. Good. Let's go up and down the rows. Brett. Riley.
Gold.
You got it. Naya. Maven.
Argon. Oh, silver.
Yes, that's AR versus AG. That's a good point. Same mistake was made last period. Don't get those two mixed up. Argon and silver. All the ones that you, as you study these this weekend on your flashcards, break them into groups. If you're struggling with all the C's, get your carbon, chlorine, calcium, copper, and cobalt out. And put them all next to each other. And just study those 5 until you know that CO is cobalt, and CL is chlorine, and Cu is copper, and C is carbon, and Ca is calcium. Okay? And argon and aluminum and silver all start with A. Get those ones out that are confusing and break them into little groups until you master them. We're up to you, Noah. Good. And Darius.
Silicon.
And Blakely. It's hard to find because it's buried down there right above. Yes, it is. And David. And Peyton. Krypton, the planet Krypton. Good job. Make sure you know those. There's a fair number of them on the test on Monday. Also, if I tell you the symbol, you should be able to tell me the name. Okay? So for instance, I say PB. Yeah, if I say PB, lead. And if I say K,
Potassium.
good. And if I say MN, Darius.
Manganese. Oh, magnesium.
You combine 2 of them. Which one?
Magnesium.
No, that's Mg. Mn is
Oh, Mn. Manganese.
manganese. Okay, it's got 3 syllables. Manganese. Okay, not mayonnaise.
Manganese.
Okay, let's look at the bell word questions here. I want to work through these with you, and this is good practice for what we need to know on Monday. So we're starting with question number 85 on page 100 and something or other. And it says, write each element's orbital notation and complete electron configuration. So this is beryllium. So we're going to put little boxes here. 1s, 2s, and the orbital notation looks like this. Okay, we're going to put 2 electrons in the first energy level, s orbital, 2 electrons in the second energy level, s orbital, and we're done. This is beryllium, right? This only has 4 electrons, so we're done. Now the second half of the question says write the electron configuration for this. So it's going to be 1s2, 2s2, and that's it. Everybody see the relationship between these 2. Electron configurations don't show me spin, and they don't show me which orbitals these electrons actually go in, but these ones do. So they both have a different purpose depending on what we're trying to illustrate as far as where these electrons are. The second one is aluminum. Okay, so we're going to need a few more boxes for aluminum. How many electrons, Darius, for aluminum?
13.
Okay, so I'm going to start by putting my 1s, my 2s, and my 2p orbitals here. Each box represents one orbital. And we're going to start adding electrons. Now the Aufbau Principle says I got to fill the 1s before I go to the 2s. So I put 2 electrons in here, and now I'm in the 2s. Aufbau Principle says I got to fill the S, before I fill the P. So I put these 2 next, and then I go to my P orbitals. Now which principle says I got to put this one, and this one before I start pairing them up? David? Hund's rule. Okay? So I'm going 2, 4, 5, 6, 7, 8, 9, 10. And we're going for where? Aluminum. So now I got to go 3s. 2 more. And then 1 more over here, 3p. And so on. It's only got 1 electron. Okay, so this is the orbital diagram for aluminum. 2, 4, 6, 8, 10, 12, 13. And aluminum is atomic number 13. How would we write this out? We're just going to go 1s2, 2s2, 2p6. We just combine all 6 of those together. 3s2, 3p1. Very good. Next one. Nitrogen. Okay. This one's shorter than aluminum, so I got 1s, 2s, 2p. We got 2 electrons, hydrogen, helium, lithium, beryllium, boron, carbon, whoops, nitrogen. There we go. I did them in the wrong order. 2, no I didn't. Yes I did. What did I do wrong? 1, 2, 4, 6, 7. Undo. Okay, there we go. Let's put this one here. 2, 4, 5, 6, 7. Okay, so we've got 3 electrons in the p orbitals, 2 electrons in the s orbital, 2 electrons in the 1s orbital. So we're going to write 1s2, 2s2, 2p3. The last one here on number 86, 5 sodium. Okay, so start the same way again. Okay, so I got 1s, I got 2s, I got 2p, I got 3s, and I got 3p if I need it. Okay, so we start. Aluminum, sodium is number 11, so we got 2 electrons. I got 2 electrons in each of these. 2, 4, 6, 8, 10, 11. Done. I didn't need the p orbitals. Okay. And we're going to go 1s2, 2s2, 2p6, 3s1. 3s1. Questions? None.
Nitrogen, how come we didn't put it up there with the 2p? How come it's only?
Okay, nitrogen has 7 electrons total. So I've got 2 here in 1s. That's hydrogen and helium. I've got 2 here. That's lithium and beryllium. And then I go boron, carbon, nitrogen. I'm at 7.
Oh, okay.
Okay. Oxygen would add a second one here. Chlorine would add a second one here. Or fluorine, sorry. And neon would add another second one here. Okay.
I get it.
And remember, it's Hund's rule that says everybody gets their own bedroom before I need to start buying bunk beds, okay? Riley?
Oh, for sodium, do we write the boxes for 3P even though?
No, I thought I was going further than that, so you don't need to. Here's the thing about orbitals, guys. Orbitals do not exist if there's no electron to fill them. Because remember, what is an orbital? Curious.
A prediction on where the electron will be.
What's the mathematical word for that?
Hypothesis? Oh, probability.
Probability. So an orbital is a mathematical probability that we will find an electron in a certain piece of space. So it does not exist until it needs to exist, until there's an electron to take up that space. Like, what's the probability that there's a car in the parking lot at midnight when the campus is completely locked up on a holiday? 0. If there's no cars here, there's no probability that anything exists, right? There might be if somebody left their car here or broke down, but I mean, it's essentially 0. Okay? Good job. Now, number 86 says use the noble gas notation to describe these electron configurations. So somebody give me the one for krypton. Rightly? Tell me what to write.
We're just going to brackets
Just like that?
Yes, it is. This side.
Absolutely. She's absolutely right. Yes. Can it be that easy? Yes. Letter B, phosphorus. David.
B in brackets.
What goes in brackets? Oh, I thought you said indium. I'm going, no, not indium. You're way out there. Neon. Yes.
Three S two. Three E.
Good. Okay. So he's got neon. So that wipes out the first 2 rows. And then we're in the 3rd row. That's where phosphorus is. So I'm going to go 3s2, sodium, magnesium, and 1, 2, 3. Aluminum, silicon, phosphorus. Those 3 electrons are in the p orbital. Remember your p block. S block, p block. S block on the left, those 2. P block on the right, those 6. You guys see it? Darius? Okay. Next one is, oh, good for you. Go.
1s squared.
I need something in brackets if we're using one of these noble gas shortcuts.
Okay, KR,
Okay. What's that thing called?
krypton.
Yep.
Okay, now it would be 5s squared.
Say 5s2. They're not exponents. Okay.
Sorry. And 4d, 2. Yeah.
Nice. Everybody see where he got that? Why is it D? Because zirconium is right there in the 2nd column of the D block. Here is my D block. Okay, remember we go here, and we're going across to zirconium, which is here. There's no F's in between. So I'm going from the S to the D, and he went 1, 2. So it's the D block. Why did he go 4 and not 5 D? Riley?
Because D block is always been
1 level behind for the D's. How many behind for the F's?
2.
2. Good job. Okay? And so let's look at the last one here. Lead. Go ahead, Riley.
Brackets XE,
Xenon.
6s2,
Good.
4f14,
Nice.
5d10, and 6p2.
Ooh, she got it down. Nicely done. 6p2, this is lead. And just a quick thing. You know what? Lead often makes a +4 ion, which we'll talk about in a future chapter. And the +4 comes from this. It can be either +2 or +4. It either gives up these 2 electrons or those 2 plus these 2. So it can either be a +2 or a +4 ion. Those are the only outside electrons. Those are your valence electrons. So lead is right underneath carbon. So it's going to have the same valence electron count. It's going to have the same dot diagram because it's got 2 here and 2 here. 4 valence electrons. Good job with the bell work. Put that away and take out your homework from last night, please. Let's go through these questions as well. Now, number 87 goes backwards. It gives you the electron configuration and asks you what element it is. So hopefully you found these a little bit easier. But we're going to look at the periodic table, figure out where they are, and what element it is. What's the first one here? Letter A. 1s2, 2s2, 2p5. Wait. It is. Now, if you want a shortcut on these guys, you just add up the numbers and look at which element it is, okay? So 2 plus 2 plus 5 is 9. We can go up there and say which one is the element number 9. It's fluorine. Okay. But for now, I mean, it actually is better at practice if you look at the periodic table. So if you can figure out 1s2, hydrogen helium, 2s2, lithium beryllium, and then go 1, 2, 3, 4, 5, fluorine. I found it. Yeah. Okay. Letter B, argon plus 4s2. Brett? Yep. Look at where argon is over here, and then roll to the next row and go 1, 2. Calcium. Xenon plus 6s2, 4f4. Peyton, you want to give it a shot? It is ND. You can just tell me it here. So let's go back to this periodic table here so it's a little easier to see. So here's xenon. We roll to the next row. 6s2, 4f4, Nd. Neodymium. Those are those little magnets they make. Those synthetic magnets. They call them rare earth magnets that you can find in the stores. They're really strong, like the one hanging on the side of that I hang my bag on every day. That's a magnet. It's really cool. Okay, next one is krypton plus 5s2, 4d10, 5p4. You can just give me the symbol if you found it. David? Tellurium. Nicely done. Te. Okay. Number E, radon plus 7s2, 5f13. Darius? Not FM. Virginia? MD, it's the doctor one. No, it's Mendelevium. It's named after the guy who gave us the periodic table. MD, Mendelevium. Okay, where is that? It is back here, right there. MD. Right there, okay? It's right next to Nobelium, which is named after the guy who gave us the Nobel Prize. If you've ever heard of the Nobel Prize, they give one out every year in medicine, in science, in politics, peacekeeping, something like that, and in arts, I think. So you got Nobel, that's a famous guy. Mendelevium, Fermium. FM is the guy who gave us a bunch of physics stuff. Enrico Fermi. Einsteinium, everybody should know him. Okay, and then we got one named after the state of California, Californium. Places and people for the most part, but also some countries. Okay, and we got one more. What's that monster at the bottom? It's really not that hard. There's bromine. Okay, bromine or bromine, your choice of pronunciation. Number 90. Draw an electron dot structure for each of these. Hopefully you flew right through these. They're as easy as counting on the periodic table how many valence electrons they got. Here's carbon. Back to black here. Number 2, arsenic. Now, if you don't want to look for arsenic, just go scroll up to the top. Arsenic is under the same group as nitrogen. So nitrogen's got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Right? It's always going to be the number between 1 and 6. I mean 1 and 8. So you can't have more than 8. You can't have less than 1. How about polonium? I believe this one's named after Poland, by the way. Polonium is way down here underneath oxygen, about the 5th row to 6th row down. Polonium, so it's going to be the same as oxygen. So oxygen has 6. 1, 2, 3, 4, and then we pair up 2 of them. 5, 6. Like,
When you start pairing up, does it matter where you put the dots?
nope. No, I put 2 up here or 2 go. It doesn't. I don't know of any rule. There might be one in the books, but I don't know anybody that enforces it. Okay. It doesn't matter which side has the 2 on. No. Number potassium, group 1, and barium, group 2. Now there is some debate about how we should do barium because both of those electrons technically are in an s orbital, so should they be together or separate? This textbook does it this way, so I'm going to stick with their convention, okay? I'm not going to argue with you about which side the dots go. Questions about dot diagrams? Okay, don't forget, you should be able to also draw Bohr diagrams for these. So if we're doing carbon, okay, carbon in the middle, 2 electrons, first energy level, 4 electrons, second energy level. Don't forget how these things look. They match up with these. Also, you had the multiple choice questions. Let's go through this. Cosmic rays. Okay, cosmic rays are not on my electromagnetic spectrum, but technically they are to the right of gamma radiation. Remember, our electromagnetic spectrum goes radio waves all the way up to gamma radiation. Cosmic rays are off the chart to the right, okay, so they're even more intense. So we're going to use the formula here for cosmic rays. What is the frequency? David? D is the correct answer. Let's stop here for a second and come back to this in a minute, so don't put it away. Let's go through our quizzes from the other day that I may need to get back, and we'll review these 2 math problems while we're at it. Here, take this, David this, liquid this, there's this, Nora this, Gia, David, Naya, Brett. Okay, let's go through these questions. Number 1. In s orbital is the shape of a dumbbell. Somebody tell me
This is
what is wrong with this statement. What is wrong with A? Megan?
They're
Okay, s orbitals are spherical. Which ones are dumbbell shaped? Noah? P orbitals. Okay, so false. Number 2, as the amount of energy decreases, its wavelength increases. Now let's think about this for a second. Here's a wave, okay? And we know a couple things about waves. We know the frequency gets higher as I go to the right. There's a chart on this quiz right here that sort of shows that. Here's your frequency increasing. We know the wavelength gets shorter and shorter and shorter. So I'm going to draw an arrow to the left up here. Wavelength is longer over here and shorter over here. So the arrow indicates longer wavelengths, higher frequency. Which direction does energy go? Since this one's asking about energy, you think, well, radio waves have more energy, or would gamma and X-rays have more energy? Yeah. okay? And that's basically which one's going to kill you, okay? Obviously, radio waves don't kill us. We've been using them for 50 years. We use them to talk on phones. We use them in our cars and in our houses. But we don't hang around gamma radiation or X-rays too much because they will give you cancer and kill you, okay? So more energy is usually the same as higher wavelength. So energy also increases from left to right. So this question says, if the amount of energy decreases this way, are wavelengths getting longer or shorter? They're getting longer. They're increasing. So this is a true statement. Okay, so that's how you need to think about this. You think about what you know about this spectrum here. We've got really long waves over here, super short waves over here, high energy to the right, low energy to the left. Number 3, total of 5 different types of p orbitals. That's true. We looked at a picture in the book, and there's 5 different types of d orbitals, 7 types of f orbitals, 3 types of p orbitals, and 1 type of s orbital. 1, 3, 5, 7. Okay, you multiply each orbital by 2 electrons, and that gives me 2, 6, 10, 14, which makes sense. That's the width of each of our blocks. Okay, a couple questions about this chart. Which type has a frequency of 10 to the 8th? That's right here, TV and FM, letter D. What type of wave has a wavelength of 10 to the negative 12th? That's up here, and that is either gamma or X-rays. Gamma or X-rays going to be here.
Boxes under us, boxes for under us or anything?
No.
Okay.
Thank you. Number 6, what type of frequency does this wave have? So I'm going to look at one wave and divide by 2 seconds, like we did on the one last week. So 1 divided by 2, everybody?
25.
Yeah. Okay, and that's why 1 per second is the same as a hertz. So the answer here is B. Okay, or you can look at this. You can say how many waves go by in 1 second. Here's the 1 second mark, and I've got half of a wave. Remember, up and down is half of a wave. Down and back up is the second half of a wave. So a full wave does a full cycle through the sine curve, if you want to call it that. Okay, what is this shape? P orbital. Which of these is correct? This one, letter A, 1, 2, 3, 4, same as carbon. Number 9, here's our 2 word problems over here. Okay, the one on the left, let me just zoom in here for a second. Okay, the one on the left is looking for the wavelength. So it says, what is the wavelength? It's in meters. Here's my lambda. You should know the speed of light, c. Have that memorized from the beginning of the chapter. Here is my new, which is wavelength, frequency. Frequency is 122.9 megahertz. Here's the formula. C equals lambda nu. And we divide by this to solve for lambda. C over nu. 3 times 10 to the 8th divided by 122.9 megahertz. And we need 1 conversion factor. We've got to get those megahertz into hertz. So how many hertz in a megahertz? We've got 10 times 10 times 10 times 1,000, which is 10 to the 6th, or you can call it a million. Somewhere along the way, you're going to have to get 10 to the 6th out of that. So that's a lot of hertz, you know, in 1 megahertz. Okay? And so 3 times 10 to the 8th divided by 122.9 divided by 10 to the 6th should give you this answer, 2.441 meters. Now, I did not take off. I did write sig figs on a lot of papers, but I did not take off a point yet. But consider yourselves warned, okay? This is a constant. We do not count constants in our sig fig calculations. So I don't care if I write 3.00000 times 10 to the 8th. It doesn't count. The only one here that has sig figs is this one. It's got 4. And so my answer has to have 4. Okay, so just be aware of that. On this one here, okay, we're looking for the energy of the photon in joules. We know the wavelength, and we know Planck's constant. It's given to us. And here's the formula that you were supposed to memorize about a week ago for homework. So E equals Planck's constant times nu, wavelength, or frequency. And you just multiply the two together, joules per second, joules seconds times per second, there should be a negative one up there, are going to cancel out, and we're going to leave us with joules. 3 sig figs, because this has 3 sig figs. Again, this is a constant, and we don't take constants into account when we deal with sig figs. Questions right here, please. Ask them now.
On the test, you can count off if we did the wrong sequence.
I will take at least a point off. Yes. Okay? So always look back at the information that's given. That's the best way. Ignore sig figs till you get to the end. Then look back at the numbers that are given. Disregard any constants and how many sig figs. There are very few problems we have addition or subtraction in. So it's almost always going to be the fewest number of sig figs. Up here, 3 has to have 3 down here. 4 has to be 4 down here. Maven.
I put 8.03 joules instead of like Electron. How much would you say about that?
That's just wrong. If you're off by a factor of 10 to the 19th. Is that what you meant? You left this off. That's a big problem, yes. All of them. Whatever it's worth. Yeah. 10 to the negative 34th, 10 to the 14th. Your calculator should handle this. By the way, if you're using that kind of calculator that Noah's got in his hand, you go 6.626, second EE, then hit the little negative button at the very bottom. It's in parentheses. Do not use the minus sign. Do not use the minus sign. Use the little negative button. There are different buttons on that calculator, and then put the 34 in. Okay? If you use the minus sign, the calculator does some weird things. Questions on the quiz? Pass those in, please. Guys, you're on camera, so stop talking. Okay, let's go back to the homework, because now we're doing a problem similar to this last night on the homework. Which one was it? Oh, number 1. So number 1 is going to be the same type of problem as that first one over there. C equals lambda nu. Okay? And you just plug it in with the speed of light, and you should get answer D like David said. Number 2, which is the electron dot structure for indium? Let's run through the class here. Peyton, last night's homework, multiple choice questions, page 170, number 2. It is. Number 3, which sublevel do those pictures belong to, Blakely?
B.
Yep, B, which is p orbitals. Number 4, David, how many electrons can reside in the p sublevel? 6, okay? So remember, to figure out how many electrons in each sublevel, a sublevel is a block. That's the word that the book uses for blocks. So we got the D block, 5 orbitals times 2, 10 elements. You got the P block, 3 orbitals, X, Y, and Z, times 2 electrons, 6. You got the S block, 1 orbital times 2, 2 elements. And we got the F block, 7 different orbitals, 7 different shapes, each which can hold 2 electrons, an upspin and a downspin, 14 different elements, okay? So that's the max. These are called sublevels by the book. Number 5 is a stupid question. Ignore it, wipe it from your brain. They want you to use the formula, the 2n squared formula, and come up with the answer D, okay? But there's no way that God created the universe to have 50 electrons in an energy level, so it will never happen. So it's a stupid question. Okay? My answer would be 32. Okay? But it's not an option here. So ignore question 5, and let's move on to number 6. Using noble gas notation, what is the ground state for cadmium? CD. Anybody up to Darius?
8.
6 is what?
8.
Something's wrong with A. Yeah, we're missing some S's too. Okay, your noble gas is always going to be covered, followed exactly by an S orbital. So A's not going to work. It is going to be letter C. 5s2, 4d10. Number 7, what is the element that has the ground state xenon? 6s2, 4f14, 5d6. Noah? Letter D. The Wizard of Osmium. It's called osmium. It's kind of cool. And number 8, what is the complete electron configuration of scandium? Maven? Letter A. Good job. Okay, so you got, what I usually do is I look at the end and then I start backtracking to find the problem. They all end in D1. Okay, that doesn't help. They all end in 4s2 D1. That doesn't help. Then I get 3p7. What's wrong with that? The p's can't hold 7, right? Maximum of 6. So I can eliminate B and D. And then I back up one more and I see 3s1 in the middle of something. You'll never see an incomplete orbital because of the Aufbau Principle in the middle. So get rid of that. Okay, so the answer is A. Number 9, which is not evidence that a chemical change has occurred. Virginia. Right, because of the conservation of mass. Number 10, make a graph. Number 11, which was the next one I gave you? Okay, why is this not the correct configuration for germanium? Naya.
I don't know, I wasn't here.
Oh, you aren't?
No.
Welcome back.
Yeah.
Whoa, what's this all about? Okay, I'm here after school today, at least for an hour. If anybody wants to come and do some brainstorming and work some extra problems or ask some questions about these electron configurations, okay? I'm also available Monday for short answers before school, and also today if you have a quick question at lunch or 7th period, okay? I will also be posting this video online over the weekend for all of my missing students today, and you can also take advantage of that over the weekend as well. Brett, 15. Okay.
I'll put it violates F.
So we're looking for germanium. Riley, did you figure it out?
Because the D block is always level behind.
Okay. So instead of 4d10, Brett, it should say 3d10. So those d orbitals should be one level less than the s's and the p's. So it goes something s, and then it's all the d's are always going to be one level, one big number behind the p's and the s's. Number 16, which one of these shows or violates the Aufbau Principle? I'll give you another chance. Brett?
What number?
16. Because? You're right. What's wrong with it?
Because the one's in the middle.
Because the s orbital only has one electron, right? And you can't have the s orbital have one electron and start filling p orbitals until all the s's are filled. Aufbau says s has to be full before I go to p has to be full before I go to d has to be full before I go to f. Number 17, which one shows beryllium? Darius. B. Really easy. B. Number 18, student performs an experiment. What is his percent error? Who calculated this? Darius? It is E, 3.05%. How would you calculate it? 37.2 minus 36.1, divide by 36.1. Okay, take those two numbers, subtract them, take the absolute value, divide by the accepted value. Maybe? Will that be on the test? Well, it's something we should already know, like for our lab reports and that we learned back in chapter 2. It's a review question. I will not answer that question. Number 19, which method of set, is there anything in this book that's not going to be on the test? I'm not going to answer that question, because everything is always free game. I try and stay with the chapter maybe, but it doesn't mean I can't throw a review question in occasionally. Darius,
D, distillation.
19 is distillation, good job, that's a review question as well, okay? Okay, so, bell work done, homework done. Quizzes reviewed. Let's go back in last week's homework assignments. There was some problems you had to do, and I wanted to double check some of your answers to see how you did. Number 5, 6, and 7, did these go back like 2 weeks or so? Did anybody ever do 5, 6, 7, 8, 9, 10, 11, 12, 13, 14?
Last one I got is 29.
What number?
Page 145, page 14, page 185, page
15 through 20. Yeah. Okay, those are really old review questions. I suggest you go back through these. 1 through 4, real quick questions about the electromagnetic spectrum. Basically, you're using that equation over there. I'll run through the answers if you want to check them. Number 1 is 6.12 times 10 to the 14th hertz. Number 2, 2.61 times 10 to the 18th hertz. Number 3, 3.00 times 10 to the 8 meters per second. And number 4, the lambda was 3.17 meters for the first one, 366 meters for the second one. First one's FM frequency, and the second one's AM frequency. On page 143, there's some more calculations using the speed of the electromagnetic spectrum. Okay, letter A was 4.19 times 10 to the negative 13th joules. Letter B, 6.29 times 10 to the negative 20th joules. And letter C, 6.96 times 10 to the negative 18th joules. Number 6, the blue sky color question should be 4.42 times 10 to the negative 19th joules. 10 to the negative 19th. And number 7, 1.59 times 10 to the negative 24th joules. On page 145, 8 through 14 were content questions. I don't think there's anything I really want to go through there with you. The answer to number 13 was a math problem, 3.70 times 10 to the 27th. On page 155, there's some more content questions. About Bohr's model, basically. Compare and contrast Bohr's model with the quantum mechanical model. One assumed that electrons were going in orbits, and the other one figured out what? It's a mathematical probability that those electrons exist in a certain location. So the whole quantum mechanical model, what we call the electron cloud theory, is the fact that those electrons have a probability associated with them. And that is whose wave equation? Tell me the guy. David? No. Whose wave equation? No. Whose wave equation?
Planck?
No. Whose wave equation? No. We watched a video last Friday about this, and the whole thing was about him and his work. And the guy drew a little picture of this guy, and he came up with all these mathematical formulas that were like 8 pages long. And his name is? No. No. Yes. Everybody say Schrodinger.
Schrodinger.
He is the hero of this wave model. Everybody make sure you get it fixed in your brain. Please. Schrodinger's wave equation. It is a thing this long. Many of you gasped when you saw it on the video last Friday. That's Schrodinger's map. Okay. Number 21 on page 160. We've got 3 minutes. I want to do 1 or 2 of these with you. This is good practice. Write ground state electron configurations for the following elements. Let's pick a fun one. How about antimony, Sb? Okay, where do we start? Who wants to rattle this off? Sb, number 51. Darius, go.
1s squared.
2. They're not squared. These are not mathematical formulas. Keep going.
2s2.
Yeah,
2p6.
good,
3s2.
good,
3p6.
perfect.
4s2.
Got it.
3d10.
Nicely done.
4p6.
Okay,
What am I on?
keep going.
5s2.
Good,
4d10.
okay,
5s3. I mean 5p3. That's what I meant to say.
Oh,
okay, let's see. 5, 1, 2, 3, 4, 5. 5s2, 4d10, 5p3. It's done. Did everybody see how he did that? He just worked through the whole periodic table and until he got to Sp. It goes Sp, level 3, Sp, level 4, 4s2, 3d10, 4p6, and then level 5, 5s2, 4d10, 5p3. Blakely?
Can you do when this like has the F but it's not in the F? Like the answer's not in the F?
Like,
Like PO.
sure, polonium. You're up. This is the last time I ask a question like that.
I don't know how to do it, that's why.
Okay, where do I start?
Okay, 1s2,
Good,
2s2,
good.
2p6,
Yep,
3s2, 3p6,
okay,
4s2, 3d10,
yep,
4p6,
good,
5s2,
yep,
4d10,
yep,
5p6,
perfect,
6s2,
okay, okay.
4f, 14,
Yes,
then 5d10,
yes,
and then 6p4.
perfect! Likely gets a star. Okay, so always remember this, okay? And again, if you have to remember that she did perfect. Perfect. She got S and went straight to the F once you get down here. You don't need to worry about the F's until you get down to level 6. Okay? 6S, 4F, 5D, 6P. Perfect. Proud of you. Okay? If everybody can do that, like polonium, like we just did, Maven.
Are we going to get that here?
No, you're going to get this one, but it has a big kind of arrow here that points and says this goes right here. It's very obvious. You just need to remember, okay? Have a great day, guys. Have a great weekend. Bye, people in TV land.